Good afternoon. My name is Zachary Sharrett, and I'm here to give you a short video on an organic chemistry topic which I'll be discussing for the next 20 to 30 minutes. Before we get started on this video, I'm going to assume that the audience is familiar with kinetics as learned in a second semester general chemistry course, specifically things like reaction rates and things like intermediates and overcoming activation energies. I'm also going to assume that the audience has an understanding of thermodynamics, which is also covered in general chemistry and also some in the first semester OChem, as well as focusing on things like temperature and heat-related aspects of chemistry, along with the overall energies associated with chemical reactions and what makes molecules versus other molecules have lower overall energies. I will also assume you're going to know the addition to alkenes, but I will be showing you more of this as we go on. So let's go ahead and get started. The topic that we'll be covering in this short course will be electrophilic addition to nonpolar pi bonds. And I'm super excited to cover this because electrophilic addition to conjugated dienes, which is the specific example that I'll be talking about, is an amazing example since it gives us the opportunity to see how these kinetic and thermodynamic factors play out in a single reaction and dictate the ratio of products observed. All of the lectures I do are discussion-based, so I'll be doing this demonstration as if I'm lecturing to a class, and I'll be fielding questions and asking for audience participation at certain points. Feel free to ask questions at any time if you can get a hold of me. Let's start off by looking at the reaction of 1,3-butadiene, which is a conjugated diene, which I'll draw in the transposition because it's a little bit lower in energy. 1,3-butadiene, and we're going to look at the reaction with the Bronsted acid, deuterium bromide. Now, in this reaction, we're starting off with a symmetrical conjugated diene. So it doesn't matter which of these set of pi electrons will attack. So we'll have this pi electrons attacking the deuterium, which pushes these electrons on here. And we have two options for where the deuterium can add. We can either add at this position here or this position here. If we had the deuterium at this position here, this would be what we call anti-Markovnikov addition, and it would put a positive carbocation at the terminal end with no stabilization. So that's very, very unlikely. So we should see that this position for the deuterium to add will not happen, and we can show that this here would be the position for the deuterium add. What this leaves us with is an allylic carbocation, which is resonance stabilized. We can show that if this pi bond here moves up here, we can then show through resonance stabilization that we get this product here. And that does put a primary carbocation here, but once again, due to the fact that it's resonance stabilized, we can move this down and it can go back up there, so it can happen. Now, what happens is the bromide will come in and can attack at this carbocation position, which would give us this product here. Or if it attacks at this position here, it will give us this product right here. This one right here is called 3-bromo 1-butene. This product here is called 1-bromo 2-butene. Now, in this addition reaction, this product is called the 1,2 addition product. and I'll be referring to it as the 1,2 addition product throughout the talk. This one is called the 1,4 addition product. Did I have a question? Okay, so this student asked, why is this called the 1,2 addition product and this called the 1,4 addition product if this name is 1-bromo-2-butene? And you know what? That's a very good question. I can see why people can get confused, and I always encourage my students to ask questions, because if you're confused about something and that starts to like weigh on your mind, you start thinking about why is that 1,2 versus 1,4. Now you start thinking about that. You don't pay attention to the lecture. 2 minutes later, you're lost, and now you can never catch back up. On top of that, if you have a question, there's highly likelihood that someone else in the class has that question. So I always encourage my students to ask questions. Now let me get to that explanation. If we look at this, the position where the deuterium at, we're going to call position 1. So this is position 1 here. We'll number the carbons 2, 3, and 4. And as you can see, the deuterium and the bromide add at position 1, 2, so we call it the 1,2 addition. In this one, deuterium adds at position 1, 2, 3, 4. You can see we get 1,4 addition product. So when we refer to it as the 1,2 addition product and the 1,4 addition product, that's relative to where the deuterium and the bromide are adding. The naming follows, IUPAC rules, and they don't think about what was added. So in this talk, when I say 1,2 or 1,4, that's the things that I'll be referring to. Now, what's really interesting about this is we observe both of these products in this reaction. And the amazing thing is not only do we observe both products, but we can make it so that one product over the other is the major product just by varying experimental conditions. So let's say that we start off with this 1,3-butadiene, and we have two situations, okay? One situation, so when we add DBr, if we do this reaction at 0 degrees Celsius with short reaction times, what we see is for the 1,2 addition product, we see this ratio be 75% of the 1,2 addition product, and we see about 25% of the 1,4 addition product. Okay? If we increase the temperature to, let's say, 40 degrees Celsius and give it a longer reaction time, we'll talk about this a little later, why we do that, we will see in the 1,2 addition product, it flips, and we end up getting about 15% of the 1,2 addition product and 85% of the 1,4 addition product. This is a pretty amazing thing. We didn't change any of the solvents or anything. All we did was decrease the temperature or increase the temperature, and we can basically see these products flipped. The major and the minor product ends up getting flipped. So let's first take a look at the low temperature situation. It looks like at low temperatures, the 1,2 product dominates. To figure out more of this, let's take a look at the allylic carbocation intermediates that we have in this reaction. Okay, so let me go ahead and make some room here. So these are our intermediates, and what we can see is in the 1,2 addition product, we have a secondary carbocation. In the 1,4 addition product, the intermediate has a primary carbocation. Now, based on this, can anyone tell me why this would be the major product at low temperatures? Any thoughts? You in the back. Okay, so what they said was the 1,2 addition product is a more stable intermediate than the 1,4 addition product, and that's a very good thought. We see higher percentage of the 1,2 addition product because this carbocation intermediate is a little bit more stable when we have a secondary carbocation versus a primary carbocation. And that was an excellent observation. So what we can do is we can think about this in terms of an energy level diagram. But before we do this, in the beginning of this talk, I talked about kinetic versus thermodynamic control. So let's go ahead and label which one is which, okay? So with kinetic control, the kinetic product is influenced by the rate of product formation, and it gives us the product that forms the fastest. So under kinetic control, we typically do things at lower temperature. So the 1,2 addition product is going to be what we call the kinetic or kinetically favored product, okay? The thermodynamic product is influenced by the most stable of the products. And if we look at our products, we'll talk about this in a little bit, but it turns out that the 1,4 addition product is the overall lower energy product, and I'll let you guys think about that. So what we see is at higher temperatures, when we have more energy available, hence the longer reaction times, it ends up giving us a chance for the reaction to occur. The 1,4 addition product is going to be the thermodynamic product. So what this tells us is the product, when we have more energy, is going to go and give us whichever product is the lowest in energy. The kinetic product, when we have lower temperatures, there's not a lot of energy available. What happens is that reaction proceeds through the intermediate that maybe, where we're going to talk about some things like activation energy and things like that. So let's go ahead and take a look at an energy level diagram. So I'm going to erase this right here. And as we look at this, what I'm going to do is what someone said in the back was that this intermediate was lower in energy than this one. So what that means is if we draw an energy level diagram showing the reaction coordinate from the allylic carbocation intermediate, we have, let's do this in a different color. Let's go ahead and show an energy diagram with energy on this axis and the reaction progress. And whenever I write RXN, that stands for reaction. When we look at this, this is actually there's two activation energies that must be overcome. The first one is the addition of the deuterium, but for both of these reactions, they both have the same energy, so I'm going to leave that one out. Now, with the once they get to the carbocation intermediate, we're going to call that the allylic carbocation intermediate. They're both at intermediate. What happens is in the 1,2 addition, and let's go ahead and do the 1,2 addition in pink. Okay, for the 1,2 addition, since this carbocation intermediate is lower in energy, the activation energy that it has to overcome, let's just arbitrarily say that this is the energy barrier that it has to overcome, okay? This here is the activation energy that it needs to overcome. Since this carbocation intermediate is more stable than this one, if we label the 1,4 addition in orange, okay, this is higher in energy. Starting from the allylic carbocation intermediate, we have to go a little bit higher, so we have a higher activation energy to overcome in this case here. The fact that at low temperatures, where there's not enough energy to overcome, what happens is the reaction pathway is going to prefer the lower activation energy, which ends up giving us this 1,2 addition product that we see right here. Now, that's great. But for when we increase the temperatures, now we have more energy available. What can happen is, and we give it longer reaction times, in this first one, in the kinetic, under kinetic conditions, we do short reaction times. And basically, with not enough energy, this is an irreversible reaction. So as the reaction goes, it takes over the lower activation energy, and it gives us our 1,2 addition product in a 75% to 25% ratio, as we can see here. So we get a lot more of the kinetic product. We still get some of the 1,4 addition product, even under kinetic factors, but in general, we see about a 3-to-1 ratio of the 1,2 product to 1,4. Now, the thermodynamic product is typically the most stable product. So if we go ahead and look at the higher temperature situation, what happens, and we let this react a little bit longer, now we have sufficient energy. That first activation energy may not be that big a deal. But when we look at our two products, we can see that, well, let's see, the thermodynamic product actually is a lower energy product. So when we give it time, and with the extra time and the higher energy, even if in this route here, if the reaction goes to the 1,2 addition product, since we have extra heat, it's able to go backwards. So this reaction is said to be reversible, whereas this reaction is irreversible. Okay, so while we look at this, we can see that even in the thermodynamically favored conditions, even if the reaction goes to the 1,2 addition product, as we let it react, it can go back and forth, and eventually it'll be like, oh, look at here, the 1,4 product is lower in energy. Let me go back to the allylic carbocation intermediate, and then since I have enough energy to get there, I can jump over this higher activation energy and go down and make the most stable product. I have a question in the back. Someone asked me, why is the 1,4 addition product more stable than the 1,2 addition product? And this is an excellent, excellent question. So let's go ahead and think about this, okay? In this, what is our final product? Our final product of the 1,2 addition gives us a mono-substituted alkene, okay? The 1,4 addition product gives us a di-substituted alkane. And you may ask, what does that matter? Well, you should have learned in first semester OChem that the more substitution on an alkene, the more stable it is. This is due to a factor called hyperconjugation. Basically, to give you a little lesson on hyperconjugation, we can think of this, these pi electrons. If we think about it, you know, we have these pi bonds that are interacting in this way over here, okay? And we have pi bonds that are interacting over here. Now, if we look at this, what can happen is if we draw out the extra hydrogen over here, and we draw out our hydrogens over here, what ends up happening is these alkyl groups on either side of the pi bond can orientate themselves to where the sigma bonds between the carbon and the hydrogens can actually donate and give more stability to these pi bonds. And in the fact that it's a di-substituted alkene, you have stabilization coming from hyperconjugation on both sides. Whereas this one, we only have stabilization on one side. Therefore, that's why the 1,4 addition product is lower in energy than the 1,2 addition product. I hope that answers your question. Now, this is kind of similar to why a conjugated diene is lower in energy than an unconjugated diene. Another study that further confirms this is if you were to do this reaction under kinetic conditions, low temperature, and shorter reaction times, you do it at low temperature, you'll see the major product being the 1,2 addition product. But if you take those products and you heat them up to a higher temperature, you'll actually see the ratio of 1,2 to 1,4 shift, and because you're heating it up, even though it was over here and it was said to be irreversible, when we heat it up, it gives it more energy and it forces it to where it can go back to the allylic carbocation intermediate, and now we can see the 1,4 addition product ends up becoming the greater, the major product in this case. This experiment where we do the reaction under kinetic conditions at low temperatures and then allow it to raise to higher temperatures, and we end up seeing a higher amount of the 1,4 addition product, shows that the 1,4 or thermodynamic product is the lower energy product, which helps us believe this energy level diagram. Let's re-explore the kinetic product, or the 1,2 addition product. Now, someone said earlier that the 1,2 product had a lower activation energy, as seen from these two intermediates here. And they said because this was a secondary carbocation and this was a primary carbocation, that's why the activation energy was lower, and that's why at low temperatures this was the major product. And this was a very good observation, but what happened was some people argued that with the addition of DBr in the initial reaction, so let's say in this, what they said was the reason that the bromide adds to the 2 position over the 4 position wasn't because of the lower energy of the transition state, but more because when the deuterium adds to position 1, the bromide is in closer proximity to this carbocation, so it just simply adds to the 1,2 over the 1,4 due to proximity. This led us to a very elegant experiment done by the Norlander group from Case Western Reserve University in the late 1900s, which was an excellent example of how data can drive further experiments. So one good thing about science is, as you're doing experiments, you have a hypothesis and you can base your study on that. But when some data comes up, or if you have some conflicting explanation, you can do an experiment to try and further prove that. So what we're going to look at is the reason that the 1,2 addition product, the major product at low temperatures, because the allylic carbocation intermediate has a lower transition state here, or is it simply due to the proximity of the bromide being added over here? So what we can do is we systematically change the experiment to see what happens. And in this experiment, I'm gonna have to erase the board. In this experiment, what they did was, instead of taking 1,3-butadiene, what they took was 1,3-pentadiene. So in this case, we added this carbon here. They actually did the experiment with deuterium chloride instead of bromide, but we're just switching the halogen. And what happens is, the results of this experiment is, when they did this experiment, they got 2 results. One of them was, they got 2 products. I'm sorry. One product was the 1,2 product, and the other product was the 1,4 product. Okay? So we have the 1,2 product and the 1,4 product. I'm going to give you a second to think about this. They observed both products. Which one do you think was the major product? Go ahead and think about this. As it turned out, they ended up getting a 75% ratio of the 1,2 product and a 25% ratio of the 1,4 product. You might wonder, how is this any different than the other experiment? And let's go ahead and look at the transition state to explain that. Now, in this case here, they saw that this pi bond was the one that attacks here. And what you end up getting is this intermediate, which can be resonance stabilized with this intermediate right here. Take a second to look at that. Do you have any idea how this differs from the other experiment? If you recall, in the other experiment, when we had this resonance stabilization, as we see here, it went from a secondary carbocation to a primary carbocation in 1,3-butadiene. In this case, the addition of this extra methyl group makes it so we go from a secondary carbocation to a secondary carbocation. So now that argument with the product being done because it was a lower energy transition state is no longer valid because both of these carbocations are secondary. The fact that we see 75% of the 1,2 product versus 25% led them to believe that the Cl is adding to this position here, the 1,2 position, as opposed to the 1,4 position due to proximity of the chloride ion as opposed to the higher activation energy to jump. So this was a little taste of one of the organic chemistry topics that I am presenting to you today. Thank you very much for your time, and you have a wonderful afternoon, evening, or whatever it is for you. Mahalo.